So if you are ready, we can begin chapter 5. So far we have talked about charges at rest. In this chapter, however, we will start talking about what happens when charges start to move. We called this electrostatics. So as of right now, may I call this electrodynamics? Charges at rest or charges moving? I will also call it magnetostatics, but that comes later. So right now, we're just going to call these. The other thing is this that I want to talk about. What do these symbols mean to you? What's the delta mean?
A change in something.
Good. And what does Q mean?
Charge.
And what does 0 mean? None, right? Okay, so in fact, what this is saying is charges cannot be created and or destroyed if we don't do anything to them, right? This is called the conservation of charge. So that's important. That's what I want to start with. But then what happens when charges start to move? So I want you to draw a table. And suppose I divide this study in 2 parts. So first part, I want to say magnetic fields acting on moving charges. And I want to divide this study into 2 parts. What happens when you have one charge? And what happens is when you have a collection of charge? Contained somehow. And I'll define that in a second. Okay, so here I want you to divide this further into 2 parts. And I want you to say general case. And I want you to say circular case. And here, I want you to further divide this into a wire, a surface, and volume. Calling it a 3D region. Okay, so moving back to the first case. Suppose you have one charge, and I'm going to call that charge Q, and that's just moving in a B field. The force acting on that charge moving with velocity v from intro 1, what do we know? F equals QV cross B. If the charge is positive. And how do we determine the force? The right-hand rule. If this is the charge, it's moving here. And if the B field is into the paper, you use the right-hand rule, right? V, B, and the direction of the force will be up. In general, we call this FB. Now, what happens if this is a negative charge? So same exact scenario, but the charge itself is negative. And the B field is exactly the same into the paper. Where will be the force? Up or down? Down. Good. FB points down. The easiest way to think about it is, I always do this. I will find what the force is due to a positive charge, because that's the equation I have, V cross B, and then I'll just flip it. Number 2. And that is important for people who are working on cyclotrons or particle accelerators, etc. In which case, you have charges moving in a circle, say with radius r. In that case, you can write sigma F is directly proportional to the magnetic force that's acting on the charge itself. This side will become MA equals QVB, where V and B have to be 90 degrees in order for this to work. Or this will be MAC, going back to intro, 1, or MB squared over R equals QVB, or in general, the cyclotron radius will be given by MV over another term. What is MV? Momentum. So that means R can be written as momentum divided by QB. Put it in a box. Another term that becomes important for this case is called angular frequency, which is omega equal V over R, or QB over M. And the cyclotron frequency, which is F omega over 2 pi QB over 2 pi m. So example 5.1 and 5.2. I'm not going to do it here, but please make sure you guys do those.